So let's conclude coordination chemistry by talking more about the colors, why we see the certain colors of transition metal complexes. So here is our color wheel in terms of the light that is reflected at each wavelength within the visible light region. So if something absorbs all light, all visible light, it will appear black to the visible eye in color. If none of the light or colors are absorbed and it's all reflected, then it appears white in color. And the color that we see, it just means that all the other colors within the visible light region were absorbed and only one color is reflected. So in this example, we have this yellow sheet. It looks yellow in color, so yellow is the only color that is reflected. All other colors are absorbed. All other colors are absorbed. So to determine where our transition metal complex, what photons or what light regions it absorbs, based on the color that we see, we know that it absorbs in the area that is complementary to the color that we see. So if something absorbs light, right, in this indigo blue region, then it would appear orange or orange red to the visible eye. So this is a solution of, don't remember the name of the solution, but it's copper in copper complex with some ligand. And the solution appears blue because it absorbs photons in this indigo blue violet region. Not absorbs, I'm sorry, that's the light that is reflected. It absorbs light in this orange red region. So those colors are absorbed and all other colors are reflected, which is why we see this blue solution. So the main takeaway here is whatever light is absorbed, we don't see it. Whatever color we see means that that light is not absorbed and it is reflected. So let's just look at a couple examples of transition metal complexes. There's three complexes here, right? We have chromium, iron, and cobalt. And all of these, right, all of these transition metals in this complex have partially filled d orbitals. And remember from last week, partially filled d orbitals will result in some color. So these partially filled d orbitals of each of these transition metal ions give rise to these three different colors. Here's another example. We have hexa aqua iron 2 sulfate on the left and potassium hexacyanoferrate 2 on the right. So both of these contain a D6 iron octahedral metal center. So it's iron 2 as the Lewis acid or the metal center for both of these transition metal complexes. And the iron 2 is D6, right? There are 6 electrons that are filling this d orbital. So even though they are both D6, they absorb photons in different ranges of the visible spectrum, so they result in two different colors. Now this last example, these are two examples of copper complexes. On the left, we have a copper 1 complex that has a fully filled d orbital, right? D10 configuration. And then this copper complex on the right is complex with nitrate as well as water ligands. And this copper 2 complex has a D9 configuration, so it's not fully filled. So that is why we see this blue color, right? That's the color of the visible region that is reflected. All the other colors are absorbed. Whereas when we have this fully filled d orbital, right, these tend to appear colorless. So this concludes coordination chemistry.